Hi everyone! Today, we're diving into one of the most essential techniques in machine learning, principal component analysis, or PCA. Think of it as a powerful data architect that allows us to reduce the number of dimensions in our data, keep the most important information without losing the soul of the dataset, make data easier to visualize. Let's take the example of the famous iris dataset. It has 4 features: sepal length, sepal width, petal length, and petal width. The dataset has 4 dimensions. We can't easily see 4 dimensions. PCA solves this by reducing the dimensions while keeping the most important information. Essentially, we're going to take those 4 features and compress them into just 2 new ones: principal component 1 and principal component 2. The process follows 5 main steps. 1. Standardize the data. Because features often have different scales. Imagine one feature ranges from 0 to 1 and another from 0 to 1,000. Without standardization, the large-scale feature will dominate the PCA results. 2. Compute the covariance matrix. It helps us see relationships. A positive covariance means both features increase together. A negative one means they move in opposite directions, and near zero means no relationship. 3. Find eigenvalues and eigenvectors. Eigenvectors represent the directions of the new axes, such as PC1 and PC2 in PCA. If we visualize the data, PC1 is the direction along which the data has the maximum spread. Eigenvalues represent the magnitude of variance captured by each principal component. A larger eigenvalue indicates a more important component, as it captures more variance from the data. 4. Select the top components. We pick the components that capture the most information based on eigenvalues. 5. Transform the data. Finally, we project the original data onto these new axes. Now let's build PCA from scratch. First, we load the iris dataset and use Standard Scaler. It is a pre-processing tool used to rescale your data so that it has a mean of 0 and a standard deviation of 1. Next, we compute the covariance matrix. Here, you can see that how different features vary together. Next, we calculate the eigenvectors and eigenvalues using the covariance matrix. We sort them in descending order because we want the components that capture the maximum variance first. If you sum the eigenvalues, you get 4. Why 4? Because we have 4 features, and since we use Standard Scaler, each feature starts with a variance of exactly 1. By looking at the first eigenvalue, 2.91, we can see that PC1 alone captures about 73% of the total information. This proves that PCA is doing its job, packing most of the dataset's story into the very first component. Combined, PC1 and PC2 preserve 96% of the total information. This is the key insight. We reduced our data from 4D to 2D, but lost almost no information. So what exactly is a principal component? It's a mathematical combination of our original features. In our output, PC1 looks like this. Notice that petal length and petal width have the strongest positive weights. This tells us that PC1 is primarily driven by the size of the petals. If a flower has a high PC1 score, it's a big indicator that it has large petals and a long sepal. Now, look at PC2. Here, the weight for sepal width is -0.923. It completely dominates this component. This is a great insight. While PC1 captures the general size and petal information, PC2 focuses almost entirely on the variation in sepal width. Finally, we pick the top 2 eigenvectors as our principal components and use the dot product to project our original scaled data into this new 2D space. Now, let's look at our visualization. Notice how isolated setosa is on the far left. It is completely linearly separable from the other groups. This tells us that its physical characteristics, now captured by PC1, are significantly different from the other 2 species. While there is a bit of overlap between versicolor and virginica, we can see they are much more similar to one another. While PC1 does the heavy lifting by separating the species horizontally, PC2 provides the fine-tuning needed to distinguish them vertically. Together, these 2 components give us a clear map of a 4-dimensional world on a simple 2D plot. To summarize, principal components aren't just original features, they are brand new, artificial variables designed to maximize variance. By using PCA, we reduced 4 dimensions into just 2, retained 96% of the information, and gained a clear visual understanding of our data. If you found this from scratch guide helpful, Hit the like button and subscribe for more deep dives into the world of machine learning. The link to the complete code is in the description. See you in the next one.